from this one, from this theorem. So we know that if we have a vector, we in the chapter 2, we already learned in the chapter 2 that if we have a vector v that can write as the linear combination of the c v1 blah 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 to c and vn, okay, and where the set of the v1 to vn is the basis for the bit for some vector space v. Oh, okay, some vector space v. So we can define the coefficient. No, we can define the coordinate vector of v, right? Can you remember the the coordinate of v respect to this basis? Okay, I let this basis is s. The coordinate vector of v respect to the basis s is the n tuple of the coefficient, right? So this is the knowledge from chapter 2. Okay, so what about this one? What does it mean? It means that if S is orthogonal basis, so we can find the coefficient vector, the coordinate vector of u respect to the basis S, right? And we know the formula like this. The coordinate vector of u respect to S, this one is the n tuple like this here, blah blah blah. The first one is the inner product of u and v1 divided by norm of v1 square, and and for the n term is the inner product of u and vn divided by vn square, norm of vn square. Okay, so that's why this leads to our remark. Okay, what does it mean? It means if we know that the set S is orthonormal or orthogonal, so we can find the coordinate vector of u, okay, by using this formula. Okay, so let's move to our exercise or our example. So if we let v is equal to 0, 1, 0, v2 is the minus 4 over 5, 0, and 3 over 5. And v3 is the vector 3 over 5, 0, and 4 over 5. So we know that the set of v1, v2, and v3 form is an orthonormal basis for R3, okay, with the Euclidean inner product. So find the coordinate vector of v 1, 1, 1 respect to S. Okay, what does it mean? It means that if we let the coordinate vector of the vector 1, 1, 1 respect to S, okay, so and this one is so I let this one to be the coordinate of the ABC here, and then what does it mean? It means this one is it means 1, 1, 1 is equal to A times v1 plus B times v2 and C times v3 here, right? Okay, this is the meaning of the coordinate vector of 1, 1, 1 respect to S. Okay, so how to find it? So because we know that the v1, v2, and v3 form an orthonormal basis for R3. So we will use the formula that we will use this formula, right? So we need to find the inner product of 1, 1, 1 with v1, 1, 1, 1 in v2, and 1, 1, 1 with v3. Okay, so this is our solution. Okay. we find that the inner product of if we let v is the vector 1 1 1, so the inner product of v and v1 is equal to 1, and b is inner product of v and v2, and this one is equal to minus 1 over 5, and c is the inner product of v and v3, and this one is equal to 7 over 5. Okay, so the answer is the triple of 1 minus 1 over 5 and 7 over 5. Okay, if you need to copy this page, so please pass it. Okay, next we will move to next example. Okay, so this example we have two questions. Okay, we need to show that W1, W2, and W3 like this W1, W2, W3 form an orthogonal basis for R3 with the Euclidean inner product, and use that basis to find an orthogonal basis by normalize each vector. Okay, this is the question number 1. And the question number 2 is express the vector U as the linear combination of orthonormal basis vectors obtained in 1. Okay, so before we do the question number 2, so we need to do the question number 1. Okay, so the question number 1 is very easy. How to check that the set of W1, W2, and W3 is orthogonal basis. So the number 1, you need to check that the set of W1, W2, and W3 is orthogonal. Okay, so the solution is very easy, right? So we find the inner product of W1 and W2, W2 and W3, and W1 and W3, and we use the Euclidean inner product because the problem gives it. Okay, so each value, I mean the inner product of W1, W2, W2, and W3, and W1, W3 are equal to 0. So we can. So the set of the W1, W2, W3. So we define this set to be S. Okay, S is an orthogonal set, and so this implies that S is linearly independent, right? We already have theorem. Okay, and since the dimension of R3 is equal to 3, and 3 is equal to the number of the element in the set in set S. Okay, what does it mean? It means that S is a basis for Rn. Oh, actually, before we say that S is the basis, so we need to make sure that S is the subset of R3. Okay, but it's quite so it's obvious that S is a subset of R3. Okay, so that's why we can conclude that S is the basis for R3. So from this one, we conclude that S is an orthogonal basis for R3. Okay, and next we will use the set S to find an orthonormal basis. Okay, so we find the norm. We find the norm of W1, W2, and W3, and we know that the norm of W1 is equal to 2, and norm of the W2 is equal to 3 times square root 2, and the norm of W3 is equal to 4 times square root 2. Okay, and so we normalize it, and we obtain that this set. Okay, we normalize each vector. So the set of W1 over norm W1, W2 over norm of W2, and W3 over norm of W3 is equal to this set. Okay, and this set is orthonormal basis for R3. Okay, so this is the answer for question number 1. Okay, and for number 2, we need to find to express the vector U is the 1, 2, 4 to be the sum of this one, right? Okay, so how to find it? Actually, this one is like so when you need to find this one, so you need to find it's like you find the coordinate vector. Okay, so you can show that A is the u, the image of the u with with the first one, the first vector. Okay, and is equal to 2, and B is the inner product of u with the second vector, and is it, and B is equal to 5 over square root 2, and C is the inner product of the u and the third vector, and this one is equal to C is equal to 3 over square root 2. Okay, so we can show that u is equal to 2 times the first vector plus 5 over square root 2 times the second vector, and plus the 3 over square root 2 with the third vector. Okay, it's not hard. So if you need to copy this page, so please pause it. Okay, we will move to we will move to next. I mean we will move to next theorem. Okay, we know that we know that if we have if we have a vector here. So before we move to next theorem, so I need to talk something. Okay, so we know that if we consider the R2 space here, okay, and we let a vector u here, okay, so this one is the vector u, and this one is the x axis and y axis. So you can see that if we have a vector u like this, so we can find the orthogonal complement of u, right? What is the, so we can find the two vectors here. Vector, this one I call this one is w, and not blue one, okay, use the green one, is w perp here. Okay, and from this one we know that u is equal to w plus w perp, right? Okay, and actually we can find the vector u, we can find a vector w, right? So if you can remember that the vector w is, actually we call this one is the projection of u on the vector this one is the projection of u, but you can see that the projection of u is the projection on the x-axis, right? Okay, so you can see that if we have a vector u, we can write the vector u as the sum of projection and the orthogonal complement, right? So this one is the example in R2. So our question is, if we move to every vector space, so if we let any element in every element in that space, so it can be expressed u as the sum of w plus w perp, where w is the element in some vector space, and w perp is the element in the orthogonal complement of w, or not. Okay, so the answer is yes, you can do that. Okay, so this one we call the projection theorem. Okay, what is the the projection theorem, what does it mean? It means that if we have w is the finite dimensional subspace of inner product space V, and then we know we have the every vector u in the vector space V can be expressed in exactly one way, as u is equal to w1 plus w2, where W1 is in W and W2 is in W perp. Okay, so if so from this theorem can be drawn as the picture like this. Okay, what does it mean? It means that so this one is the vector u, right? And if we let the plane, we do the plane with b to be subspace w, so we protect the vector u on w here. Okay, and we can find this vector, right? The vector that orthogonal to the projection of u on w. Okay, so this one is so this vector, I mean this one, the red one, is the vector in W perp. Okay, so this is a picture for this theorem. The proof of this theorem is quite tedious. Okay, but I will open the proof. Okay, we open the proof. So I will discuss about the I will discuss about the proof briefly. Okay, so how to do that? Before we start to prove the projection theorem, so we assume, so because the W is the finite dimensional vector space, what does it mean? It means the element of the basis for the W is finite. Okay, so we will let the set of V1 to VR to be the basis for W, but we will add something. We will add some condition to this basis. So this basis we assume that this basis is an orthogonal basis for W. Okay, but from our assumption, so we have a question that why we can assume that W has an orthogonal basis. Why? So for the answer of this one, so I will not give you the answer now. Okay, I will not give you the answer now. Okay, so this is how to prove it. So the proof is quite I mean it's quite complicated. Okay, how to use that. Okay, so from this one, so we consider this vector. So this vector is the u minus of this vector. So the question is, where is this vector come from? So this vector come from W. Okay, so we need to find some vector that some vector in W. Okay, and you can see that if we set y to be u minus this vector, then the inner product of y and vi is equal to 0. Okay, we will use the property of the inner product. Okay, so it's not hard. Okay, so from this one so this one y inner product of the y and vi is equal to 0 for all I. What does it mean? It means that y is the element of the W perp, right? Why the vector y is the element for the element in the W perp, because y, the inner product of y and vi, is equal to 0 for all I, and v1 to vr is the element of the basis. Okay, so that's why we can conclude that the vector y is the element in W perp, and we let the vector x to be this vector. Okay, and we know that the vector x is in W. Why? Because x can write is the linear combination of v1 to vr, and this one is the element of the span of the v1 to vr is equal to W. So we can show that u is equal to y plus x when x is come from W perp and y is come from W perp and x is come from W. And next, so we need to show that So we need to show that we need to show that y and x are unique. Okay, so how to prove it? So how to prove the unique for the uniqueness? We let y prime in the perp and x prime in the build such that u is equal to y prime plus x prime. Okay, then we we have x plus y equal to w, and w is equal to x prime plus y prime. Okay, from this one we move x prime to the left hand side and y to the right hand side to obtain that x minus x prime equal to y prime minus y. Okay, so this question, what does it mean? It means that if you focus on the right hand side, we know that y and y prime is the element in W prime in W perp, right? And we know that W perp is the subspace of the vector space V. Then x minus x prime is the element in W perp. Okay, and since x and x prime is the element in W and W is a subspace, then x minus x prime is the element in the W. What does it mean? It means that x minus x prime is the element of W and W perp, right? But we know that the intersection of W and W perp is equal to the set of zero vector. What does it mean? It means that x minus x prime is equal to 0. Okay, and this implies that y prime minus y is equal to 0. So that's why we can conclude that x prime equal to x and y prime equal to y. Okay, this is our proof for the projection theorem. Okay, if you need to copy this page, so please pass it. Okay, next. Okay, from this theorem, we are talking about the projection of the vector u on the W. Okay, so in this theorem, you find it tells us that we can find the position of u on the W by using this formula. Okay, so if S is if we have W is the subspace of the inner product space V, okay, and S is the orthogonal basis for the W, then we have the position of vector U on the subspace W is equal to this formula. And if S is orthogonal basis for the W, then we can reduce that the position of vector U on the W is equal to this formula. Okay, the proof the proof is obtained from the projection theorem. Okay. Okay, before we prove this theorem, so we need to have some picture here. Okay. What does it mean? What does it mean? What does it mean of this vector? This vector. So you can see that if we have a vector u here, so this one is vector u. Okay. So if you project on the subspace V here, so this one is, what does it mean? What is this one? This one is the projection of u on W, right? And because if we know that the W is spanned by two vector v1 and v2, so we can write so we can find that the projection of u on W is the sum of the projection of u on v1 and the projection of u on v2. Okay, so if we see this picture, so the meaning of this picture is like this. Okay, so how to prove this how to prove theorem. Okay, the theorem is very easy. Okay, for number one, we assume that S is an orthogonal basis for the view. Okay, and we let any vector u in V. Okay, so by projection theorem, we there exists the projection vector u on W, and this one, the projection of u on W is the element in W, right? And the vector and some vector x in W perp such that x plus the projection of u and W equal to u. Okay, and because S is an orthogonal basis for W, so we already find the formula of the element in this vector, right? So that's it. Okay, and for the number two we will use number one. Okay, and because of S is an orthogonal basis, so the norm of V, the norm of each Vi is equal to 1. Okay, that's it. Okay, if you need to copy this page, so please pause it. Okay, we will move to some remark. So from this one, we know I think all of you can remember about the projection vector of u on V that we already learned in M4, right? Can you remember that? If we have a vector u and vector V here, so we can find the projection, right? The projection of the vector u on V is the red vector here. Okay, so this one is the projection of u on the vector V, and we have the formula for the projection of u on V, right? Is the inner product of u and V over the norm of V square times vector V. Okay, so what does it mean? It means that the formula from the previous slide, from the previous theorem, is the general form for this one is the general formula for the vector space. Okay, and so we can find the projection, right? So what about the orthogonal complement? Can we find the orthogonal complement of the vector u? So how to find it? Okay, we move to this page. So from this one, we know that the vector x is the element in W perp, right? And we know that x plus projection of the u on W is equal to u. Then we can find that x is the u minus projection of u on W, right? What does it mean? It means that if we can find the projection of u on W, so we can find the orthogonal complement of u by using u projection of u on W. Okay, and the formula is the x equal to u minus projection of the u on W. So if we draw a picture, the picture is like this. So you have the vector u. Okay, so this one is the projection of the u on W, and this one is the u minus projection of u on W. Okay, we'll move to next example. Okay, this one. Okay, so we let R3 have the Euclidean inner product, and W will be the subspace that's spanned by the orthonormal vectors v1 and v2. Okay, so the question is find the component of U that orthogonal to W. What does it mean? It means that now we uh now we know that W is the span of v1 and v2 here. Okay, W is span of v1 and v2, and uh and we need to find this vector. Our vector U is the x plus the projection of the U on W. Okay, so we need to find the vector x. Okay, so you can see that if we can find the projection vector of U on the subspace W, so we can find the complement or component of U orthogonal to W. That is the vector x. Okay. Okay, so we start to find the projection. Okay. Since we know that the set of v1 and v2 is orthogonal basis for W. Okay, then we can find the projection of U on W by using this formula, right? And actually, you can see that this formula is not only orthogonal, it's orthonormal. Okay, I mean v1 and v2 is orthonormal. Okay, so that's why that's why the denominator is equal to 1. Okay, so we find the inner product of the 1 1 1 and 1 and 0 1 0, and this one is equal to 0. This one is equal to 1. Okay, is equal to 1. And next we find the inner product of 1 1 1 and minus 4 over 5, 0 and 3 over 5, and we obtain that is equal to minus 1 over 5 here. Okay, and we calculate this to obtain this vector. This vector is the 4 over 25, 1 and minus 3 over 25. But we need to find the orthogonal or the complement of U orthogonal to the W. So we will use the projection of U on W, right? So we use the U minus the projection of U on W, and the equation and the answer is this vector is the 21 over 25, 0 and 28 over 25. Okay, that's it. Okay, if you need to copy this page, so please pause it. Okay, so I think from example that we already talked. Okay, we already talked in this video, so you can see that if we have a basis that orthogonal, or we have orthogonal basis, so you can find the orthogonal complement of orthogonal. I mean, you can find the complement of vector that orthogonal to the subspace easier, and you can find the coordinate vector easy, right? So